Hi everybody, hope you are wonderful today. This is part 3 of chapter 18, and we are going to talk about equilibrium. So last time we discussed collision theory, and we said particles need to collide with enough kinetic energy and the correct orientation in order to have an effective collision that causes a reaction. So the activated complex, or the transition state that is at the top of an energy diagram. Let me draw a quick energy diagram here for you. So let's see, let's put it right here. There's potential energy and time. So these are your reactants, products, transition state or activated complex, right? And your activation energies right here. So the activated complex or transition state, because it has such high energy, it's pretty unstable. But once it forms, because it's unstable, it decomposes, turns into something else. And what happens is that once you form this, it is just as likely that you are going to form products, which is what's expected, or you could reform the reactants. If you remember when we talked about the transition state, we had an example where we said, well, let's say I have H2 and Cl2 reacting to form HCl. So if you remember, I drew this on the board. This was a little bit ago. Like there's my H2, for example, and there's my Cl2. There's my two HCl's. We said the transition state is kind of like in between the reactants and in between the products. It's where the reactant bonds are starting to break and the product bonds are starting to form. So once I form this, I could, continue to break these bonds and form the other ones and form HCl. Or I could just break, this bond and reform my H2 and Cl2. So both are just as likely. So that's what this is saying here. And this is why most reactions are reversible. You could form the reactants or you could form the products. So reversible reactions obviously do not go to completion, because when you are done, some of the reactants have turned into products, but some of the products went back to turn into reactants. So at the end of your reaction, you have some reactants and some products. To show that it's a reversible reaction, like let's look at this. If I take some SO2 with oxygen, they react together to form SO3. But then SO3 can go back and decompose to form SO2 and O2. So instead of writing two reactions like this, what we can do is write it as one reaction, one equation, but then do a double arrow like that. One going up to the right and one going to the left. So we say that the reaction that's going to the right, so the SO2 combining with the O2 to form SO3, that is the forward reaction. And the SO3 decomposing to form O2 and SO2, that is the reverse reaction. Together, this is a reversible reaction. So again, the one going to the right, this is your forward reaction. The one going to the left, that's your reverse reaction. You put them together, that is a reversible reaction altogether. So chemical equilibrium happens when no net change occurs in the actual amounts of components of the system. So one of the labs that we're going to do, I'm going to go to it here. In the equilibrium lab, if we were to do it, we had like these beads that kind of fit together. I can't remember what, I think they're called like, what are they called? Like lock-in beads or something like that. You have like this bead, but then it has like a little part to it that comes out and a hole on the other side. And so they kind of interlock together. So you take two beads and interlock them together. We used to use them like as little kits to make like little bracelets and chains and stuff like that. So anyway, what you do in this lab is it's a 4-person lab. So one person is supposed to be the forward reaction. So what you do is you take 2 of the individual little beads. So you would take, there's one, there's a second one. And your job is the entire time to put them together to make A2, right? So this is 2 of the A's, 2 of the beads, and then this is one product where it's A2, where 2 of the beads are interlocked together, right? So that's the difference between 2A versus A2. So the first person, every time we do this, for a whole minute, they just keep putting them together to make the A's into A2s. Then there's the reverse reaction. So the second person, their job is to take, every time we make an A2, they separate them from each other to make the 2 A's. So you're the reverse reaction. Now to make this a little bit challenging, because it is easier to separate than to put together, we blindfold that person. Third person is the timer, so they count 1 minute increments. And then the fourth person is kinetic energy. They shake the bin to make it harder for both of them to find the little beads. So this is kind of an example of what you would see happen. Initially we start with 100 little beads. They're all separated, so we don't have any product yet. And after the first minute, this is not correct. This should say 4 and this should be 92, not 98, I'm sorry. So we end up with 92 of the separate ones, and we've made 4 of the A2s, right? After a second minute, now we've made 6 of the product molecules, and now we have 88 left of the individual. Third minute, 7. Fourth minute, also 7. Fifth minute, 8. Sixth minute, 10, 11, 14, 14, 15, 15, 15, 15, 15, 15. Oh, what are we seeing? We're seeing that this remains the same. Now, the reason for that is at the beginning, you have just all A's. So the forward reaction is pretty fast, right? It's making more and more and more. But then now that you've made enough of the A2s, the reverse reaction can be fast as well. It starts out slow because that person has none to work with, and then now they have more and more and more. It's easier for them to find those A2s to separate them. At some point, the speed of the person going from two A's to A2 is just as fast as the person going from A2 to A, again, because this person has less to work with, so it's harder to find those, and this person has more to work with, so it's easier to find more. So at some point, their rates equal to each other. That's when you've reached equilibrium. When their rates are equal to each other, because the rates are equal to each other, the amounts do not change. So let's go back to, actually no, let's not go back. Let's look at what this would look like in terms of a graph. So if I were to graph the concentration of the reactants in the products. Let's start with the reactants. The reactants, so the A's, start pretty high, right? And they go down, and then they become steady. So they start out at 100, they decrease a little, and then they become steady. The concentration, so this is my reactants. My products start out, the A2 start out at 0, and then they increase, and then they become steady. So this is the products. And they just keep going. Once they become steady, so right here and on, we have reached equilibrium. We know that because our rates are equal to each other and the concentrations remain the same. Their concentrations are not equal. Like right now, at equilibrium, we have more reactants than we do products, right? Some reactions are going to be the opposite. So you could have this happen. That's meant to be steady. So this is your products, and this is your reactants. That could happen as well, right? So in this reaction, here's your equilibrium where they remain steady, but you do have more products than you do reactants. So at equilibrium, what is equal is the rate of the forward reaction and the rate of the reverse reaction. Those are equal. The concentrations remain the same, but the concentration of the reactants and the products are not necessarily equal. Okay, let's talk about the rates. So if I were plotting the rates, so these are concentrations, right? I forgot to label that as concentration. What if I was graphing the rates? So this is time, by the way. All of these are time. I'm sorry, I did not label them. So the forward reaction. The forward reaction, taking the 2A's going to A2, that starts out pretty high, right? Because all I have is reactants here. So my reaction rate is high. And then it slows down, and then it remains steady. So this is the forward. My reverse reaction starts out really low because I don't have any A2s to separate, right? So it starts out at 0, but then look at that person, speeds up, but then the rate remains the same. Oops, I'm sorry, I messed up. You know, I can't draw. There we go. This is the reverse. So notice that at equilibrium, here's when I reach equilibrium right there, my rates are the same. So what's the same about equilibrium? Rates, not concentrations, but rates. Okay, so this here is telling you even though the rates of the forward and reverse reactions are equal at equilibrium, the concentration of the components on both sides may not be equal. And so some reactions are going to be product favored, meaning that I have more products at equilibrium than I do reactants, even though the rates are equal, but I have more products than reactants. Others, I'll have more reactants than products. And so we saw that with my two graphs here. Here I have more reactants than I do products at equilibrium. Here I have more products than I do reactants at equilibrium. All right, hope this helps. Our next topic is going to be Le Chatelier's principle. Have a wonderful day.